Good morning, Chem 20s. Our lesson today will be on applying pH and concentration to previously learned formulas. It is important to be able to apply the concept of pH and hydronium ion concentration to other previously learned chemistry concepts, such as dissociation or ionization equations. If we take a look at this example, a 300-gram sample of hydrogen perchlorate gas is dissolved in 400 milliliters of solution. Calculate the hydronium ion concentration and calculate the pH of this solution. So the first thing we're going to do is we're going to write out hydrogen perchlorate as a dissociation equation, or I guess an ionization equation because it's an acid. So hydrogen is a 1 positive charge. If I check my table of polyatomics, perchlorate is a 1 negative charge. So we're going to have HClO4 gas. And again, the Arrhenius's revised definition of an acid says it's going to be in water. So we're going to donate a proton over to the water. So that's going to get us a hydronium ion, as well as we're going to be left with perchlorate ion. Now, we are given a mass of hydrogen perchlorate. Again, I know it dissociates because it's a strong acid. Strong acids, if we think of the idea of major entities or biame, they're going to break down. We're just doing it in acid form where the water is taken into account here. And so I can, using the mass of hydrogen perchlorate, I can find the moles. So it is mass over molar mass. So I'm going to take 3 grams, divide it by, and this guy would be 1.01 plus 35.45 plus 16 plus 16 plus 16 plus 16. So he adds up to 100.46 grams per mole. So 3.00 divided by 100.46, enter. I have 3 sig figs, 4 sig figs, so my answer is going to be in 3, 0.0299. It's going to round up, and this is going to be in moles. Now that I know the moles of hydrogen perchlorate, I can find the concentration. Again, because it says we're going to end up with 4 liters of solution, so we're going to dissolve it in that. So I have moles per volume. This is going to be 0.0299 moles over 0.4000 liters. So divided by 0.4 liters. And again, in 3 sig figs, I have 0.0747 moles per liter. Now, if I remind us of what I would do in this case in previous, hopefully you remember that when we go to do this, right? This is the concentration of the perchlorate. So this is going to be 0.0747 moles per liter. And I am now going to use that value to write a concentration statement. If I know the concentration here, I can find the concentration of the hydronium ion, and that's going to answer my first question. So to find the concentration of hydronium, take the concentration you know, 0.0747 moles per liter of HClO4. And this is, again, when we play our little game of leapfrog, I'm going to multiply by 1 mole of hydronium. And I'm going to leapfrog back and divide by 1 mole of HClO4. So moles cancel, perchlorate ion cancels, so I'm going to be left with 0.0747 moles per liter. My last statement is I calculated the hydronium. Now I can find pH. And using our new formula, pH equals the negative log of the hydronium ion concentration. So that's going to be the negative log of 0.0747. And again, we want to use the full calculator number. And so negative log of that value. And if I look 3 sig figs, 4 sig figs, so I'm allowed 3 decimal places because this is a pH. So this is going to be 1.127. No units on pH. Now, if I was to assign marks, 1 mark for the ideally revised dissociation equation, you would get a half mark for formula, half mark for substitution, so that would be 1 mark. You would get a 1 mark for answer, half mark for formula, half mark for substitution, so you'd get 1 mark, 1 mark for answer. You wrote the concentration statement for 1 mark, and again, you calculated the pH for another mark, and I would probably give an additional mark for 3 sig figs, 3 sig figs, 3 sig figs, 3 decimal places. Units are everywhere, states are correct. So a question like this would be out of 1, 2, 3, 4, 5, 6, 7, 8 marks in the future. Now, with what we've been doing with formulas, we've been using pH to solve for hydronium ion concentration, and we've been using POH to solve for hydroxide ion concentration and vice versa. There is a connection between pH and POH as well. There's also a connection between hydronium ions and hydroxide ions. However, we're not going to actually share those connections until we get to chemistry 30. So we're going to strictly keep with pH and hydronium ion together, POH and hydroxide ion together. No connection between the two categories yet. For both pH and POH, an inverse relationship exists between the ion concentration and the pH or POH. For example, the greater the hydronium ion concentration, and that would be going this way, the lower my pH is going to be. And you can see when I look on here, although they're calling them hydrogen ions instead of hydronium, right? They're using the old original Arrhenius definition. We can see that as we go start at neutral distilled water, we have a perfect balance of 10 hydrogen ions, 10 hydroxide ions. They're going to be balanced because it's neutral. They're going to cancel each other out ideally. Well, when I go more acidic, what happens is we gain more hydrogen ions, hydronium ions, and less hydroxide. Because remember, acids, don't really want hydroxide ions. They kind of refer to a base, but because they are dissolved in water, there's always going to be a very minuscule amount of hydroxide present anyways. Same with when we go down on here, or we go to a higher pH, you will see that my hydroxide ion concentration is going to increase. Now, you'll notice I have a hydronium as well. Again, that is due to the presence of water.